I'm Andrew, and my partner is Luke, and we accidentally deleted our intro video, so that's why you have this weird still frame right here. But that's me on the left and Luke on the right, and for our project, we built a spectroscope and used it to examine the spectra of various temperature-rated LED lights. So the principles behind our design are pretty simple. Light enters through the small slit in the front, travels through the cavity where it hits the diffraction grating on the other side. Our diffraction grating has 1,000 lines per millimeter. It's pretty standard. And it works because the diffraction angle of the incoming light is dependent on the wavelength. So when the incoming light is composed of multiple wavelengths, they diffract at different angles, which creates a spectrum of color. And we just use the iPhone camera to capture the spectrum.
We use an internet application called Spectral Workbench to calibrate and record our spectra. Calibrating the spectrometer is necessary because a CCD camera records data by pixel number and not by wavelength. The calibration requires a known emission spectrum, and so for our calibration, we used a compact fluorescent light bulb that produces light by exciting mercury atoms. The spectrum emitted by mercury gas contains two distinct peaks, one at wavelength of 435 nanometers and another at a wavelength of 546 nanometers. We recorded the spectrum of our compact fluorescent bulb and then matched the pixel number of both peaks to the known wavelengths. Doing so allowed us to assign a wavelength at each pixel using a linear correction.
So here you can see our 3D design for our spectrometer. It's basically a square tube that's 25 millimeters in width and 25 millimeters in height. The top length is 88 millimeters long and the bottom length is 56 millimeters long, which creates an angle of 45 degrees with respect to the back of our smartphone. The slit through which the light enters is on the other end, and we tried to print a 0.5 millimeter width slit, but the 3D printer wasn't capable of printing in such fine detail, so we ended up printing a 2 millimeter slit and then using tape to create a 0.5 millimeter slit. So this was our experimental setup for recording our data. We had our spectroscope positioned 1 meter away from our light source, and the iPhone was connected to my computer to use the Spectral Workbench app, which allows for real-time capture, but I'm using my computer to record this, so you can't see that right now. But essentially, we started with the compact fluorescent bulb as our first light source, recorded its spectra, used that to calibrate like we talked about earlier in the video, and then we replaced the CFL bulb with the 2700 Kelvin bulb, recorded the spectra, and then repeated that process again with the 5000 Kelvin bulb, taking care that when we were switching the bulbs out, we didn't move the lamp or the spectroscope to make sure our data was consistent.
The first LED bulb tested had a color rating of 2700 Kelvin and produced the following spectrum. We note that the largest color spike is at around 600 nanometers and indicates that this color LED contained primarily red light, and the smallest peak comes at around 450 nanometers, and so this particular color contains the smallest amount of blue light. The second bulb tested had a color rating of 5000 degrees Kelvin and produced the following spectrum. This one, we note that there is a larger peak at 450 nanometers, indicating that this color contained primarily blue light, and that the smaller peaks come in at around 550 nanometers and 600 nanometers, indicating that there was less green and red light for this color LED. The third spectrum we took was perhaps the most important as it validates the spectroscopy principle. Higher energy light is more violet and lower energy light is more red. By showing the difference between the two spectrums, the principle was confirmed. The 5000 Kelvin bulb clearly contained much more blue light than did the 2700 Kelvin bulb, which contained primarily red light. In conclusion, this validates our hypothesis